analysis. Tensor analysis and a little bit of differential geometry. It's annoying. It's annoying because it's got all these indices floating around and different coordinate systems. So it's mildly annoying, but once you get used to it, it's really very simple. It is really, really simple. And it was actually made simpler by Einstein, by the famous Einstein summation convention, which means you didn't have to write summation symbols all over the place.
Question?
Yeah.
Yeah, going back to that distance on the sphere, the equation where it's cosine of whatever it is, that assumes that that little interval is flat, otherwise it's...
Yeah, that's right. We assume that small enough, yeah, that's exactly right. In both Riemannian geometry and Gaussian theory of surfaces, it is always assumed that if you look at a small enough piece, that a small enough piece looks flat. The technical statement is a small piece located at some point can be well approximated by the tangent space. The tangent space would be the flat tangent to the surface.
But it's not flat. They assume it's flat, but it's not flat. So that equation is
It's a question. Yeah, that's right. But it's a question of orders of differentials. It's a question of orders of differential. Now, differentials aren't really lengths. They're limits of small lengths. And they're defined in such a way that the square of a small thing is 0. So there is a technical mathematics to small differentials.
So is there a constraint that the function has to be continuous?
Yeah.
Because if you take 2 points at the edge of a crevice,
Yeah.
it just, geometry matters a lot.
Depends on what you mean by a crevice. Yeah, no, you're right. No, the metric tensor can always be taken to be continuous. It's often derivatives of the tensor which are not continuous. But I don't know what a crevice means. A crevice does not mean a crease. That's, of course, a crease. This space here is as flat as this space. In fact, it's exactly the same space thought of in terms of differential geometry. The distance, all right, let's be careful. Let's say exactly what we mean. The distance between any 2 points on here, between 2 neighboring points, doesn't mean the distance between these points if you go through the page. Right? It means the distance in the surface. The distance in the surface, and that distance between these 2 points doesn't depend on whether you fold the page or not. It's exactly the same with the page folded as with the page unfolded. The right terminology is we're interested in the intrinsic geometry of the page. The intrinsic geometry means those aspects of the geometry which only depend on what's going on inside the surface and not how the surface is embedded in 3 dimensions. These are different embeddings of the same surface, right? All sorts of different embeddings of the same surface. But the intrinsic relationships between the points on the surface are independent of how we bend the surface. So we're talking about intrinsic geometry, geometry that would be measurable by a little creature that only gets to move around on the surface and doesn't get to look out of the surface.
What if we try diagonalizing the metric?